Hello and welcome to this Camden BRI Connect 21 webinar on shelf life science. In this webinar, we're going to be talking through how Camden BRI's multidisciplinary team help clients to design of trials to optimize product quality and determine shelf life. Through case studies, we'll discuss how a holistic approach involving microbiological, chemical testing, physical testing, sensory and consumer analysis can guide clients in determining the shelf life of a new or existing product. Next slide, please. So the webinar today is presented by me, Peter Burgess. My role here at Camden BRI oversee the technical sensory and consumer activities across the Camden BRI group, including our sensory centre based at Chipping Camden and our consumer test centre at Leamington Spa. I'm delighted to say I'm also joined today by my colleague Gail Betts. So welcome, Gail.
Hi, Peter, and to all of you listening to our webinar. My role as a microbiological quality and safety lead is to manage a number of different teams, look at many different aspects of microbiological product shelf life. We offer advice and practical studies to help companies demonstrate that their products remain microbiologically safe and stable throughout their assigned life.
Thank you, Gail. Well, like many of our clients, we're continually monitoring the food and beverage market. In particular, we keep a close watching brief on factors that are likely to shape client requirements for shelf life assessments. Some of these factors are noted here, for example, include things like the evolution of plant-based applications, especially into different food categories. We obviously looking at the increased use of fortified and functional food ingredients. We're seeing changes in formulations influenced by both health and value considerations. And of course, we're looking at changes in packaging in response to sustainability demands, as well as initiatives that seek to reduce food waste. Next slide, please.
I think the factors that you just mentioned, Peter, help keep shelf life one of the most frequent inquiries that comes into our client technical advisors here at Camden BRI. Just as an example, here is a snapshot of the number of inquiries coming in a week in February this year. And you can see the different types of things that our clients are asking us. And the biggest aspect that comes quite often is shelf life inquiries. And the reasons for this, as you're going to explain in the next few slides, are that there are many different disciplines and different parts to shelf life testing that make it actually a little bit more complicated than people realise. And there's a lot to consider when correctly assigning a product shelf life.
Okay, so what are we referring to when we're talking about shelf life of a product? Well, the IFST's definition outlines the key considerations that must be considered when assessing shelf life. And these include things like, obviously, a food must remain safe. It's got to retain desired sensory, chemical, physical, and microbiological characteristics. And it's got to comply with any label declaration of nutritional data when stored over recommended conditions. Now, the shelf life limits of some of these factors mentioned in this definition are defined at a laboratory level without the intervention of a consumer. For example, a central issue in declaring a food to be safe is that it must be free of pathogenic bacteria, and this can be assessed through standard microbiological analysis. In other examples, for example, vitamin D in rich milk, it must comply to a certain concentration. Again, this can be measured in an analytical laboratory. Next slide, please. The ASTM standard on sensory shelf life places more focus on the product's sensory characteristics and interaction with the product by the end user. So this definition emphasized the point that shelf life is an integral aspect of the product design, in that the food must not only be safe, but it must, at the point of consumption, retain acceptable quality, which has to be maintained over a period of time. We'll come back to how acceptable quality is defined later on in the session. But in the meantime, let's consider in the first instance how we can overcome the safety and nutritional challenges that arise in determining shelf life. So it's at this point I'd like to bring Gail more fully into the session. So Gail, can you tell us a little bit more about how and your team are involved in the area of shelf life evaluation?
Thanks, Peter. I think it's useful for me to start by thinking about different product categories, because the emphasis on microbiological, sensory or chemical drivers will depend very much on how the products are formulated, processed and stored. And you can see here, we're looking at frozen foods, ambient foods and chilled foods. So microbiologically speaking, With respect to frozen foods, we do not often carry out shelf life trials for the simple fact that microorganisms will not be able to grow at minus 18 degrees C, and so you're unlikely to see any changes over life. And in fact, if anything, the levels of microorganisms will decrease during frozen storage. So from a microbiological point of view, with frozen foods, as long as the foods meet the microbiological standards at the start of life, then you can almost have as long a shelf life as you want to. The situation is very different when we start to look at ambient foods and chilled foods, because here microbiology in terms of spoilage and the growth of pathogens are much more important and can have a huge influence on the shelf life that we can achieve. And when I'm talking about microbiological shelf life trials, there are two different approaches that we use in our labs here at Camden BRI. And the difference between them depends really on whether the organisms are naturally present in the product or whether we have to grow them and deliberately add them in just to simulate a contamination event. And the two things here are shelf life trials and challenge tests, and the definitions are on this slide. So to elaborate a little bit further, if we look at shelf life analysis, all depends really what question we want to answer when we're designing these trials. So if our primary goal is to establish how long a food can remain of optimum microbiological quality under its normal processing and storage conditions, then a shelf life trial taking into account only those naturally present organisms is the best approach. But this assumes that the risk of any food pathogens or specific spoilage organisms are effectively managed by the controls in place, such as the hazard analysis. If the goal, however, is to show that that food formulation and manufacturing process can prevent the growth of a specific pathogen, if it happened to be present at the start of life, then that's when we need to use the challenge test study instead. And here, as I said, the difference is that we are deliberately taking organisms, pathogens or spoilage organisms that could have the potential to be associated with that product, and we'll inoculate them at the start of life and monitor their change throughout the storage period, so we can answer the what if question. What if it happened to have these pathogens present after a normal routine manufacturing process? And so if you're concerned with ready-to-eat foods and the risk from listeria, or if you've got extended life, modified atmosphere packed foods or vacuum packaged foods, and you're worried about the risks from botulinum, here we're still looking at whether the shelf life is right for these food products, but we will be deliberately inoculating and monitoring the growth of our pathogens as we go along. So I just want to show you a couple of documents that are very important to the microbiology team here when we are looking at shelf life and challenge test studies. The first one is an ISO challenge testing standard looking at challenge testing procedures. And it's very important when you're doing these types of studies, both microbiologically and from a sensory point of view, that you use recognized standards. So this ISO working party, I was fortunate to be part of this and helped shape this document. And it follows quite closely the protocols outlined in our own best-selling guideline 46 on microbiological shelf life, which was re-released in 2019 as a second edition. Now, what both of these documents do is to explain the scientific approach that you need to take when you're designing and interpreting data from shelf life studies. So they outline the time frame of the study, which organisms or other parameters you need to look at, how many testing times you need to do over life, and more importantly, from my point of view, is the replication that you need to do on each testing occasion. And then having done all that, you can look at your data and compare it to your predetermined criteria. Now, I mentioned the replication because it's really important that these studies are designed properly in order to give you meaningful data. And both Peter and myself are quite passionate about ensuring that the studies that we do and the data we give are relevant and meaningful. So if I just show you a slide here of some of the types of data that we can get out of microbiological shelf life testing. So there's a graph here which is looking at the total viable counts of microorganisms in a vacuum packaged egg product. And we've plotted the log count of this plate count in this egg product over storage time. So it goes between 0 and 20 days on the bottom axis. And you can see that there is a purple line, and that's showing us the average count throughout that time frame. And you can also see a dashed line at log 6. That is the threshold that we're looking for in terms of achieving a microbiological stable shelf life. So the first point at which that purple line goes over that threshold line indicates the end of shelf life for this product. But the thing I really wanted to draw your attention to was the variation that you can see in those symbols. So we have a square, a diamond, and a triangle, which represent data from our 3 replicate packs. And at the start of life, you can see they're very close together at the 0 time point. But as we move through the storage time, we can see for this particular product that we get a lot of variation in the count that we see here. And this is quite high variation for this particular product, but we do see it quite often. If we're looking at a product which has got a reduced pH or quite a low water activity, and is at the boundary for where those microorganisms can grow, because slight differences in those intrinsic parameters between packs can either allow or not allow the organisms to grow. So if, for example, you had a shelf life trial conducted with a service provider that didn't include this type of rigor in the trials that they did, you might choose, for example, the medium level pack or the lowest level pack, because you haven't got 3 replicates to choose from. You don't get an average count. You might not get a true picture of the real microbiological levels in these products. So if you're assigning a shelf life based on inappropriate data, once the product goes to market, you could start to have issues and customer complaints. So it really is important to get this level of scientific rigor in when designing these experiments. And this is something that both sensory and microbiology do here at Camden BRI. And I'll pass back to Peter so he can explain a little bit more about the sensory approach.
Thank you, Gail. The ASTM standard that I mentioned earlier gives 3 possible criteria to determine the sensory shelf endpoint. This can be a change in the overall sensory profile of the product, or it could be certain product attributes that are known or suspected to be key in consumers' perception that the product has changed, or it could be consumers consider that the product is no longer acceptable. Companies that have really stringent standards might choose the first criteria for which sensory discrimination or descriptive tests are necessary. The second criteria is needed to identify critical attributes, and once these have been identified, a trained panel can be used to monitor these changes. The third criteria, this is valid for those companies who are willing to accept that the stored products are not going to be identical to the fresh products. In this case, consumers must identify the magnitude of change that they are willing to tolerate. Next slide, please. So considering the first of these criteria, the overall sensory profile, in short, discrimination tests are designed to answer questions where there is a change in the sensory difference between the samples. Triangle tests are often the most common form of tests used to assess the overall difference. Descriptor tests are another form of discrimination tests, such as per comparison or 2 AFC tests, again looking for specific changes in a particular defect. Or indeed, difference control tests can be used to actually establish the size of the difference. Descriptive tests answer more questions in the area of in what way do the samples differ. The results from a descriptive test encompass a complete description of the product. QDA profiling is one of those examples. Next slide, please. So in both discrimination tests, consideration must be given to the testing area. So ISO standards provide us information on the test environment, airflow, decoration, humidity, etc. And there's also obviously a focus on screening and training of assessors, as well as their ongoing monitoring. So for example, Camden BRI's panel members are trained for a period of at least 6 months before their data is used in shelf life assessments. And we also have an ongoing program of something like 32 acuity tests over a 12-month period in order to maintain their performance. Next slide, please. So moving on from sensory panel tests to more effective tests, these are used to answer the question, do consumers actually care about the difference? In other words, will consumers still consider the product acceptable in spite of the sensory changes produced during storage? In the context of sensory shelf life, this can take two forms. These could be hedonic tests, usually associated with what we call a cutoff methodology, and usually measured using 9-point hedonic rating scales. The second of these are accept-reject type tests, and these are associated with survival analysis. Next slide, please. So survival analysis is basically used where we recognize that although shelf life might be determined through sensory panels, and they might be focused on looking at a sensory attribute or an analytical parameter, consumers at the end of the day may still find the product acceptable. So what survival analysis does is identifies the extent to which a product can change before it is likely to be rejected by consumers. The shelf life is estimated at the time taken to reach a predetermined consumer level of rejection. The point to note here is that this is only applicable where quality changes rather than microbial safety are the deciding factors in determining end of shelf life, and when changes occurring during the storage can be considered what we call more than subtle for regular consumers. So next slide, please. Typically, survival analysis utilizes something like over 100 consumers. These are consumers who are typical users of the product and are recruited to take part in what we call a central location test style consumer assessment. Respondents monetically assess something like 8 to 12 samples, and these typically represent different ages or shelf life applications for the product. For each sample, respondents have to indicate whether they found the sample acceptable or not. Based on the data collected, it's possible then to model the percentage of consumers that are likely to reject the product at or beyond a certain age. An optimal best before date can then be assessed. Next slide, please. So with suitable survival data analysis, we can actually construct several models in order to predict the percentage of rejection over time. The chart here illustrates the type of output you can expect to get from survival analysis. So for example, if we look at the bottom slide there, if the shelf life, for example, was set at when 25% of consumers who had accepted the fresh samples rejected some of the stored samples, using the 95% confidence interval from this chart, which is the dotted line, you can see from here that the shelf life indicated by this analysis indicates a sensory shelf life of something like 9 days. This is actually higher than the current 6 days for this particular product in this test. Next slide, please. So the benefits of survival analysis are such that you can actually assess the gap between actual and maximum shelf life and the potential for the buffer to be reduced where appropriate, along with associated benefits of reduced food costs and food waste. There are a few points to note, however. You've got to bear in mind that sample selection is important when doing these kinds of tests, so we need to make sure that the changes are more than just slightly subtle over time. We certainly need to make sure we've got a sufficient number of storage times to be assessed, including the oldest sample microbiological test results will permit. And so while a test itself is relatively straightforward, the data analysis can be a little bit more involved than typical consumer tests of its type. Next slide, please. So just before we finish, there are a few other aspects of shelf life that we haven't had a chance to fully cover at this stage. The first is chemical or biochemical changes. So Gail, did you want to expand on these a little bit?
Yes, Peter, I will. So many of the common biochemical changes that you'll see in food products will actually lead to sensory deterioration. So Peter's team will pick them up on the various different types of tests that he's just described to you. But sometimes even doing the sensory deterioration and the microbiological tests as well, there are certain aspects that we still can't adequately describe. And if we look to our biochemical colleagues, then we can see that there are different processes driving some of these changes. So oxidative rancidity is one of the biggest things that can happen to a high fatty food product. So if it's packaged in an inappropriate packaging format or atmosphere, or if there's some breach in the integrity of the packaging, such that the products with a high fat content are exposed to oxygen, you start to get this auto-oxidation process occurring. And over time, you get some sensory defects, which quite often can be described as stale or cardboardy types of flavors. So if you describe that to one of our biochemical experts, then that will be indicative that something's gone wrong with the packaging and their fat has started to go rancid. There's a lot of different enzymatic reactions that can occur in food as well. So another one looking at the fat content will be lipid degradation. So rather than something which is caused just by exposure to atmospheric oxygen, this will be as a result of any surviving enzymes breaking down the fats. So again, you'll start to see higher levels of peroxide or free fatty acids being formed. So if you have a product which is showing some of these fat degradation processes, our biochemical teams can look for some of these parameters to give an indication of what's happening. And the same is the case for some of the other enzyme reactions like proteases, which can start to cause breakdown of the protein structure, which will result in changes in the texture and flavor of the products. If you have a sauce which has been thickened with starch and it starts to break down, this can quite often be the result of amylases breaking down the starch. So again, it might not necessarily be microbial, it might be an enzyme-based reaction, which will lead to a sensory deterioration in the product. And if you have peeled fruit, which is going brown during shelf life, this can be due to peroxidases that are still present and able to cause the browning. So again, there are means and ways in which you can prevent the action of those enzymes during life to stop these defects occurring. And I think another one that a lot of our listeners might see quite often is to do with meat coloration. And again, this is to do with the atmosphere that the product's stored in. So the really bright red piece of meat that you see there would have been packed in high oxygen. So quite often meat on the shelves is packed with 70% oxygen because this makes the myoglobin present in the oxymyoglobin form, which is a really nice bright red. The other two thumbnail sketches there are showing meat which has got little bits of red but lots of brown. And so it looks like the meat is off. Well, the problem quite likely is due to the fact that the oxygen levels have dropped. And so the myoglobin now is not in that bright red oxy form, it's in a different form. And this will happen towards the end of shelf life as the levels of oxygen in the pack may reduce. But again, this instantly would hint to biochemical actions progressing and suggest some issues with pack integrity or modified atmosphere packed gases. So both Peter's teams and my teams work closely with our biochemical experts to work on all aspects of shelf life. Another point that we get asked quite often, both in Peter's area and mine, is do we really have to test over the whole of the shelf life? Can't we speed it up somehow? My product's got a 12 months life. Can't we do this in 2 months? And generally speaking, I think we're a little bit reluctant to do this because the storage conditions are an integral part of a product's shelf life. And once you start to change those conditions, and if you change them dramatically, you can cause different chemical, biochemical, or microbiological processes to occur, which might never occur in reality if you store them for their whole shelf life under their normal conditions. So as I say, we're slightly reluctant to do it. There are some aspects where you can. So if you're looking for a physical change in a product, so if you've got an oil water-based product that is susceptible to separation, if you store at an elevated temperature up to 40 degrees, you might be able to speed up that process. Or if you have pickles and sauces and you're looking for instability in the product, you can store for up to 6 weeks at 55. And again, for some biochemical reactions, such as the rancidity that I've just discussed, if you expose a product to higher than normal oxygen environments, you may speed up that oxidative process. So we can do it for some aspects, but I think we would advise that the results are used with some caution, and the more severe the conditions that you've used, the more potentially unreliable the results are. So really think about your shelf life requirements early in the process and make sure you've got enough time to get the testing done, I think is what our advice would be. So how does this all fit together then? We've discussed three different aspects of shelf life of a product here: micro, sensory, and chemical analysis. As I says, it's important at the start of the shelf life process to make sure that all relevant aspects are considered. And I think if there's one piece of advice that both Peter and myself would give, it's to make sure that you consider all of these at the start of this process, because I think quite often we will find that clients come to us just to discuss one aspect of this and don't think about all of the other things that can happen, which I guess is why it's good that we've got such a diverse team here that can fit together to look at all the different aspects. So what you need to do when you're fitting together the data that you've got is to really find the shortest time point for any of those individual factors that you've looked at that will meet your criteria and give you a safe product that is fit for consumption and meets all the required characteristics. So I've just got a slide to show you which puts together some sensory and microbiological shelf life data. So this slide is similar to the one I showed you earlier, where I'm plotting levels of total viable count against storage time. And we can see the average count here in the green line. At log 6 is our threshold for the total viable count. And at that point, from a microbiological point of view, we would say that the life was over. But on this slide here, I've also plotted the sensory data that my colleagues provided for us for this type of product as the histogram bar charts. And the red line there at a level of 4 would be the sensory cutoff value. So Peter described a cutoff hedonistic scale. And so our sensory colleagues would evaluate the sensory properties of this product and measure it from 1 to 9. And a level of 4 is the point at which it's no longer acceptable from the various parameters. So here, from a microbiological point of view, the product could have had a 9.5-day life. But from a sensory point of view, the sensory defects on some of the flavors and appearance at day 7 are becoming unacceptable. So taking both of those bits of data together, we would say that actually this product should have a maximum shelf life of 7 days. So Peter, any final thoughts from you before we wrap up this session?
Thank you, Gail. I just think I'd like to reiterate your point about the multidisciplinary nature in determining shelf life, and this is becoming increasingly prevalent amongst the clients that we're interacting with. So next slide, please. And at this stage, I'd like to say thank you very much, Gail, for sharing your experiences and insights in terms of shelf life science. I'd also like to thank everyone for listening to the webinar. If you want to find out more about some of the things we've discussed during this session, please don't hesitate to contact either Gail or myself. Our contact details are listed on this slide here. Alternatively, you can just ping an email to the inquiries team at Camden BRI. So thank you again for listening.